When you stretch some materials and then let them go, they return to their original size. But some things don't. Plastic isn't elastic. It stays stretched. It's plastic. So, what do we mean when we say that something has plastic properties? Of course, when we normally use the word plastic, we mean a certain type of material. Spaghetti may well be plastic, but it isn't normally made from plastic. So, what are plastics? Take a typical plastic. What would it look like if we could get down to see the molecules? It might actually look a bit like a plate of pasta. Plastics are made up of very long molecules, tangled up together. But how do we make them? First, we need chemicals produced from oil. To make a plastic, we need many identical small molecules containing carbon atoms. These carbon atoms join up chemically to make a chain. Plastics are called polymers. Poly means many. A single molecule might be made up of thousands of repeated units. So we need the individual molecules, called monomers. But what else do we need to make a polymer? Well, it looks like these swimmers can't form a pattern without their coach. It's the same with making plastics. We need a catalyst. Like the swimming coach, a catalyst influences the reaction, but isn't normally part of the final product.
Will you please get back into your line, nice and straight, your arms out and your heads up?
Catalysts make reactions go faster and work in a more controlled way. Different plastics are made from different compounds. But they're all long-chain molecules, so do they all behave in the same way? Take a look around any kitchen. Loads of plastic implements. But why plastic rather than metal? A kitchen has many chemicals. Think what vinegar can do to some metals. The reaction with metal is obvious, but look at a plastic straw. Does that explain why plastics are used instead of ceramics or glass? They say, if you can't stand the heat, get out of the kitchen. Thing you shouldn't do with plastics. Aha, the bowl melts. But what about that spatula? That's plastic too. Looks like we've got two kinds of plastic here. Time to go back to the pool. First, let's think about the bowl. We know it's made up of long chain molecules. And it takes many chains to make up the plastic. So what happens when we heat something? Well, heating something increases the energy in the system. The molecules move about more. So what effect does that have on the chains? They don't break up, but they do move away from each other. The whole thing becomes much more mobile, and if the plastic cools down, it sets again. These plastics are called thermoplastics. But what about that spatula? Why didn't that melt? Start of all good cooking. But the thing about butter is that if you heat it and then cool it down again, it returns to something like butter, a bit like the plastic bowl that our friend just softened. But if you mix the ingredients to make a cake and heat that, it doesn't matter what you do, you'll never get the butter back again, or the eggs or flour. Maybe that's a clue to these plastics that don't melt. Something irreversible happens to them. So what is it? Well, back at the pool, let's see if we can make one of these heat-resistant plastics. Starts off looking the same. Lots of individual molecules, the coach acting as catalyst. But watch this. Something different going on. Links are formed between the different polymer chains. And unlike the chains, these linking molecules aren't necessarily carbon atoms. But what effect does that have when we heat up the system? Here we are underwater, increasing the energy of the swimmers. The trick is that the cross-links hold the chains together, even when the plastic is heated. This is called a thermosetting plastic, because once formed, it doesn't melt. So, do these two types of plastics explain all differences in properties that we see? Well, one of these is more dense than the other, but they're both thermoplastics. If you don't believe me, heat them. See? They both melt. And what's more, they're both made from the same monomer. So how come one is more dense than the other? Time for some chemistry. We start with the monomer ethene. Like these swimmers, only two carbon atoms join together by a double bond. The chain is formed by the double bonds opening into single bonds, allowing another ethene molecule to join onto the chain. This opening of double bonds is common to all polymerization reactions. So the ethene molecules join together in the presence of a catalyst to make the polymer polyethene. The carbon atoms form the backbone of the chain. Of course, there are millions of polymer chains in a plastic like polyethene. So that's polyethene with a fairly high density. But what happens if, as the chains grow, they branch? Under certain conditions, or with a different catalyst, the long polymer molecules have branches in them. What difference does that make to the density of the plastic? So, density depends on how closely the polymer molecules can pack together. If the chains are branched, they can't pack as tightly as if they're not. But not all polymers are made from such simple molecules. Some plastics start with more bulky molecules. This is the styrene group in that familiar polymer polystyrene. What difference do you think bulky molecules like this make to the density of a plastic? So, we know a bit about the chemistry of plastics. But how do we make things from plastics? Well, it all depends on what type of shape you want to end up with. Molds are fine if you want something that's solid, but it's not much good for bottles. And solid things tend to be heavy. So what other methods could we use? Just like cooking, it's a question of choosing the appropriate type of force. But to do this with a plastic, you have to do it before it sets hard. What other ways can we use pressure to force things into the shapes we want? What type of pressure is being used here? But here, there are two types of shaping process: blowing and molding. But that's not the only combination of methods that we can use. Solid objects can be made quickly by injection molding. It's a bit like forcing the icing when you're decorating a cake. Or you can just extrude the plastic. It's a very useful way of making long lengths of a particular shape, but it's still a question of pressure. But back to our original problem of making something hollow. One way is to use the force of gravity to do the work for you. How could you do that with a plastic? Right, we've seen we can make lots of things out of plastics, but how do they compare with other materials? Well, let's see how strong a typical plastic is. But how does that compare with, say, a metal like aluminium? The metal is stronger, but metals have a very regular structure. But we know some plastics don't. Let's take a look at the force extension curve. The plastic we are stretching is a thermoplastic. Remember what that means? The molecules in the polypropylene are tangled up, but not locked together. So what happens when the plastic is stretched? Looks like there are different stages as the plastic is being pulled. So what do you think is happening to the molecules? If in doubt, go back to the pasta. At first, the molecules are all tangled up. As the plastic is stretched, the molecules become untangled. Then, when they're all untangled, it gets harder to stretch again, until it breaks. But we've seen there are two different types of plastic. Thermoplastics which soften, and thermosets which don't, because the chains are linked together. Which would you expect stronger? Well, if this pasta represents the polymer chains, let's try pulling apart a thermoplastic. Now, how about one where we've linked the chains together? One problem with plastics is they're not always very stiff. Or are they? When do you need something that's got to be light and stiff? Well, what about a surfboard? It has to float, but it has to be stiff as well. It'd be no good making it from a floppy plastic. So, what do? Well, they start off with foam. That'll certainly mean it has a low density. But what's going on here? Whatever this substance is, it's then coated in a plastic resin. Let's take a look at the finished product. The sheet we saw was made from glass fibres. They're set inside the plastic. They strengthen the plastic. And they also make it tougher. So now we've got this stiff, strong, light stuff. How big can we make things out of glass-reinforced plastic? About this big. This is the largest structure yet made from GRP. She's called HMS Brecon and is over 60 metres long. And it's not only the hull that's made from plastic, most of the superstructure is as well. But hang on a minute, why bother making a ship from plastic? The Navy seems perfectly happy with all these others being made from metal. But HMS Brecon is a mine hunter, looking for mines on the sea floor. Does that give you a clue? Plastics get everywhere. Even artists use them. In the old days, brushes would have been made from wood and hair. Now it's plastic handles and nylon fibres. Even the paints are made with acrylic polymers. But recently, plastics have got a bad name. People say they're not environmentally friendly. Now, there's a lot to be said for that argument. But let's have a think about it for a minute. Cars. Definitely not environmentally friendly, but hardly likely to go away either. So what's that got to do with plastics? Reducing fuel consumption would certainly help the environment. But how do you do it? Well, one way is to reduce the weight. And what's one of the heaviest parts of a car? The engine. A big hunk of metal. So why not make it out of plastic? Impossible? What are the problems? Sure, it's got to stand up to heat and vibration. But remember those glass-reinforced plastics. They're tough and they're heat-resistant. Have to make some of it from metal still. But on this experimental engine, all these parts are plastic. And every bit of weight saved saves fuel. So that's a plus, environmentally. Meanwhile, back at the rubbish dump, there's another reason people don't like plastics anymore. Other rubbish rots. But plastic isn't biodegradable. And some plastics seem to last forever. So what do we do? It might not rot, but it doesn't do anything else either. Remember the kitchen? Plastics are chemically unreactive. On the other hand, people are now developing biodegradable plastics like this one. But it still seems a waste. After all, we make plastics from oil, and that won't last forever. It seems ironic that we start with a mixture of long-chain molecules in oil, break them down, and then rebuild them into plastics, and then throw them away. But see this? Just another plastic? Well, not quite. This is cellulose film, one of the first plastics made, and it doesn't come from oil. The original material comes from trees. So perhaps we should be growing more trees. Isn't elastic. It stays stretched. It's plastic. So, what do we mean when we say that something has plastic properties? Of course, when we normally use the word plastic, we mean a certain type of material. Spaghetti may well be plastic, but it isn't normally made from plastic. So, what are plastics? Take a typical plastic. What would it look like if we could get down to see the molecules? It might actually look a bit like a plate of pasta. Plastics are made up of very long molecules, tangled up together, But how do we make them? First, we need chemicals produced from oil. To make a plastic, we need many identical small molecules containing carbon atoms. These carbon atoms join up chemically to make a chain. Plastics are called polymers. Poly means many. A single molecule might be made up of thousands of repeated units. So we need the individual molecules, called monomers. When you stretch some materials and then let them go, they return to their original size. But some things don't. Plastic. But what else do we need to make a polymer? Well, it looks like these swimmers can't form a pattern without their coach. It's the same with making plastics. We need a catalyst. Like the swimming coach, a catalyst influences the reaction, but isn't normally part of the final product.
Do you please get back into your line, nice and straight, your arms out and your heads up?
Catalysts make reactions go faster and work in a more controlled way. Different plastics are made from different compounds, but they're all long-chain molecules, so